Okay, friends. So this problem is essentially a recapitulation of various things that we learned in Chapter 24. Um, the figure that they give us to do in the problem is very similar to the problem in example 24-7. It's right here at figure 2419. We have an insulating sphere that's uniformly charged with a charge Q. In our case, Q is 1.11 picocoulombs, and a radius A. In our case, A is 0.1 meters, and around it is just vacuum, let us suppose. And so they've already talked about what happens inside a conducting sphere. It's right down here in this corner. You can see where in figure 2411 that we'll have the electric field start at 0 and go up to what it is on the boundary when we have all of the charge included in our problem, and then it'll fall off as a Coulomb's law type K electric Q over R squared. And I've started doing that math right up here, and you can see how far I got. I have K electric, and I've got the Q and the 1 over R squared. And now I'll bring up my calculator where I have all those programmed in, and we'll push the button and see what it gives us for a electric field there. Oh, look at that. It's about 1.999, and that's sort of what I figured because the numbers were contrived after all. At this point, we have the electric field falling off like it is over here. See how it falls off right over that area. And it'll fall off as a 1 over R squared law until it hits the conductor. And at what distance does it go out? Well, it goes out the square root of 2 times A. Why did they choose that number? Because our distance occurs in the denominator in the form of 1 over R squared. And so when you have 1 over square root of 2 times A squared, you're going to get 1/2 the electric field that you got at the surface of the insulator. So that electric field falls off and off until it hits the edge of the conductor. Well, what does it do in the conductor? Well, all of us know there is no electric field inside of a conductor. Essentially, I'm doing part C right now. So we're going to stop at this point and go back and look at part B. Part B said graph the total charge enclosed in the concentric Gaussian surface of radius r as we go out from 0 to 40 centimeters squared. Well, that's going to appear not as a straight line like we have it in figure 2411. It's going to be a cubic. It's going to start at 0 charge, and then since volume goes as r cubed, the amount of charge we have inside of our Gaussian surfaces. See down here in this part of the problem, they've given us a Gaussian sphere both first inside the problem and then later on outside the problem. Here's the inside and outside. And so we'll draw a graph with a cubic that'll go up and up and up till it hits our density, our total amount of charge, which is 1.11 picocoulombs. And then by Gauss's law, that'll stay constant until we hit this conductor surface. All the field lines have to end at that conductor, and the only way they can is to have a bunch of negative charges around the inside of that conductor. How many negative charges? Well, it turns out to be minus 1.11 picocoulombs. How come? Well, that's so that the plus 111 picocoulomb on the from the insulator and the charge on the inside exactly sum to 0, so there's no net charge inside the conductor. Now at that point, there will be no charge, 0, 0, 0. It'll go on along until it hits the outside edge of the conductor, and at that point it'll jump back up to 1.11 picocoulombs and go out from there to infinity. Here they only ask us to go out to 40 centimeters, with 0.4 meters is about twice the diameter or the radius of the conducting sphere. So that's what your graph should look like. Let's return to graph C now, which was talking about the electric field. Remember, we had it like down here in figure 24:11. We had it going up linearly till it reached the edge of the conductor or the insulator, and then it would fall off, and when it got to a half this amount, the electric field, that would be the edge of the conductor. It would drop to 0. It would go back along till we reach the edge of the conductor, then it would jump back up and continue down the curve you see there. So I hope that helps you understand how to draw the pictures asked for in 7-4.